Hi everyone. So in this video, I'm going to be going over the practice problems from this week. So there's no weekly meeting this week, and so this will be kind of like a replacement for our usual weekly meeting. I would really recommend that before you watch this video, you try to do these problems yourself. I think you're going to get a lot more out of this if you have given the problems a bit of a try before you just straight up watch me show you how to do them. So before I get into the actual problems, I want to remind you of some of the identities that we're going to be using. Now, this probably looks like a really long list, but I want to remind you that most of these are identities that we've already been working with for at least a few weeks. So, for example, the first identity here, which is the first Pythagorean identity, we learned that quite a while ago. So hopefully that's one that you have committed to memory already. I think of all of the different trig identities, that's probably like the most important one to know. And I'll come back to these next two in a second, but these even odd identities, again, those are also ones that we already learned earlier in the quarter. So hopefully you have some familiarity with those. And then this last list here, I would almost not really call these identities. This is basically just rewriting all the different trig functions in terms of sine and cosine. So these are things, again, that go back really to the beginning of the quarter when we first defined the different trig functions. The only thing really that's new on this list is these two right here. But you don't really need to memorize these two because if you know this Pythagorean identity, you can always find the other two just by going through and dividing both sides of the equation by something. So for example, if you start with sine squared plus cosine squared is equal to 1, if you divide everything by cosine squared of theta, that will give you this second Pythagorean identity, right? Sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. 1 divided by cosine squared is secant squared. So this entire second identity just comes from taking the first identity and dividing everything by cosine squared. And then similarly, if you take this first identity and divide everything instead by sine squared of theta, instead of cosine squared of theta, that's where you get this third Pythagorean identity, right? Sine squared divided by sine squared is 1, cosine squared divided by sine squared is cotangent squared, and then 1 divided by sine squared is cosecant squared. So really, those are the only two things that are new, but you don't really need to memorize those. And then one last thing, and we'll get to these a little later, are these angle addition and subtraction formulas. These I'm not going to ask you to memorize just because they're a little bit more kind of intricate. So these I will give you the formulas for them on the quiz and on future exams as well. Okay, so let's get into some questions. So the first set of questions are basically just simplifying trig expressions. And so we'll see that in some cases, we're just going to be kind of rewriting things in terms of sine and cosine. Sometimes we're going to be making common denominators. Sometimes we're going to be using Pythagorean identities. Those are really the things that are kind of in our toolbox to work with. So first one is a fairly simple example. If you have an example that looks like this, where it's really just two different trig functions being either multiplied or divided together, what I would try first is to rewrite everything in terms of sine and cosine. And that way you can see whether anything can be combined or canceled out or anything like that. So what's another way of, or how do we rewrite this in terms of sine and cosine? Well, cosine of theta is just still cosine of theta, right? There's nothing to really do to rewrite that in terms of cosine. But secant of theta, we can rewrite that as 1 over cosine of theta. So now we have cosine of theta over 1 over cosine of theta. So how can we kind of rewrite this in a way that is more simple? Well, remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And maybe let me make this a little clearer. So it's like this is kind of the big fraction, and then this is the smaller fraction within it. But yeah, so like dividing by 1 over cosine of theta, that's the same as multiplying by cosine of theta over 1. Right? Like general rule is that if you have something like A over B over C, that's the same thing as A times C over B. That's the rule that we're using here. Okay, so how do we simplify this? Well, cosine of theta times cosine of theta, that is cosine squared of theta. And then we have a 1 in the denominator. We don't need to write that. And so our final answer is cosine squared of theta. All right, so next up we have cosine of t times tangent of negative t. So again, this is a product of two different trig functions. So one thing that will be helpful eventually is to rewrite things in terms of sine and cosine. However, right now the inputs for these two functions are different, right? In order for us to really be able to kind of combine things, allow them to cancel out, anything like that, they need to have the same input, not one of them being t and one being negative t. So the first thing we want to do is use one of the even and odd identities to replace the negative or tangent of negative t with something else. So remember that tangent is an odd function. So tangent of negative t is the same thing as negative tangent of positive t. So I'm just going to rewrite this slightly nicer, bring this negative sign out front. So that's negative cosine of t times tangent of t. So now that we have the same input, now this is where it will be helpful to rewrite things in terms of sine and cosine. So cosine, there's nothing we can do there, but we can rewrite tangent as sine of t over cosine of t. And now we can see that we have a cosine in the numerator and the denominator. So those are going to cancel out and we're going to be left with just negative sine of t. And so that is our final answer. Okay, so next up we have a kind of a fraction going on. And in the numerator we see cosecant squared of theta minus 1. So anytime you see an expression that involves basically any of the trig functions being squared and being subtracted or added or subtracting 1, that should always make you think of the Pythagorean identities, and you can kind of try to see like which one might that fit in with. So I would always recommend, like at the beginning of every test or quiz, just write out all of these different ones, right? You can write down sine squared plus cosine squared is equal to 1, as we talked about at the beginning of the video. Then you can just derive the other ones from that. And so which one of these seems like the most closely related to what we're working with here? Here we have cosecant squared minus 1. So let's go look for a trig identity that looks like it might be related to that. That looks most similar to this, right? Cosecant squared minus 1. So how can we rearrange that so that instead of it being 1 plus cotangent squared is equal to cosecant squared, how can we kind of get that so it's cosecant squared minus 1? Well, we can just subtract 1 from both sides, right? Like taking this equation, if we subtract 1 from both sides, we get a new identity. We find out that cosecant squared of theta minus 1 is equal to cotangent squared of theta. So that's what we're going to use in the numerator. We can now, was it the numerator or the denominator? I forget. Numerator. So where it says cosecant squared of theta minus 1, we now know that we can replace that with cotangent squared of theta. So again, I'm not trying to tell you, oh, here's another identity you have to memorize. It's more like whenever you see something that like kind of reminds you of the Pythagorean identities, that's where you can kind of play around and just see like, how can I rearrange things so that maybe it will fit with that identity or with the expression you're trying to simplify. Okay, so now we end up with cotangent squared of theta divided by cotangent of theta. And so now we can simplify this, right? We can get rid of the square and get rid of the cotangent at the bottom, and our final answer is just cotangent of theta. All right, so next up we have, and actually, sorry, let me say one more thing, because there is kind of another way that you could have approached this, and I think the way that we did is probably the fastest. But one thing I want to mention is that in general, if you have a fraction that looks kind of like this, like a plus b over c, where you have two things in the numerator and one in the denominator, you can always split that up into something like a over c plus b over c. And so another way that you could have done this one is you could have started by splitting it up into cosecant squared of theta over cotangent of theta minus 1 over cotangent of theta. And I'm not sure how this would go, but I would encourage you to kind of try doing it this way. So maybe take these and rewrite everything in terms of sine and cosine and see where that gets you. It might be kind of circular. It might not really help you make much progress, but I would imagine that that would be another way to do this problem. But the reason I bring that up is because the next problem we're about to look at, in some ways it might seem like you can use that same splitting up idea, but it's not going to work in this case. So notice here I wrote a plus b over c is the same as a over c plus b over c, right? That's because that's the way that fractions work, right? If you have the same denominator and you add two things together, you can combine the two numerators and leave the denominator the same. What is not the case is if you have something like this. If you have something like a over b plus c, that is not the same as a over b plus a over c, right? That's just not how fractions work. Like, it's not true that 1/5 is equal to 1/2 plus 1/3. That's just not how fractions work. So just be careful that when you're working with expressions that look like this one, you're good. You can split that up into two fractions if you want. When you're looking at expressions that look like this one, it may be tempting to try to split this up and say, oh, tangent squared of x over tangent squared of x plus tangent squared of x over 1. That just doesn't work. You can't split it up that way. Okay, so how else can we deal with this? Well, kind of like the last one, the first thing that I would probably do here is I would look at this denominator and say, that kind of looks like a Pythagorean identity. Let's go look at the different Pythagorean identities and see if we can make something fit with this. So tangent squared of theta plus 1, or tangent squared of x plus 1. And in this case, we actually have one that perfectly matches that, right? Tangent squared of theta plus 1 is equal to secant squared of theta. And so that means that we can rewrite the denominator in the example we were just looking at as secant squared of theta. So we can rewrite this as tangent squared of theta, or x, over secant squared of x. Okay, so where do we go from here? Well, now we want to rewrite things in terms of sine and cosine, because there's not really much else to do, right? We use an identity. Now we just have like kind of something similar to what we had on the first problem, right? Just kind of like one trig function over one trig function. Only difference is they're squared. But yeah, let's break these down into sine and cosine. So tangent is sine over cosine. So tangent squared is sine squared over cosine squared. So we have sine squared of x over cosine squared of x all over 1 over cosine squared of x. So now this goes back to that idea we talked about earlier about how dividing by a fraction is the same as multiplying by its reciprocal. So we can rewrite this as sine squared of x over cosine squared of x, so leaving the numerator the same, but then instead of dividing by 1 over cosine squared of x, that's the same thing as multiplying by cosine squared of x over 1. And so if we do this multiplication, the cosine squareds will cancel out, and so we're left with sine squared of x over 1, which is just sine squared of x. All right, so next up, we have cosine of t minus 1 over secant of t minus 1. So again, I want to remind you of what I wrote up here, which is that we can split things up in the numerator, but we can't split things up in the denominator. So, technically you could split this up over the numerator. Like you could say, cosine of t over secant of t minus 1 over secant of t minus 1. Like that is equivalent. I don't know how helpful that would be. I'm sure you could eventually get to the right answer doing it this way, but the next step that you would end up taking going this way is kind of the same as the next step you would take without breaking it up. So I don't think breaking it up really would help. But again, what you can't do is for example, you can't like break this into like cosine of t over secant of t minus 1 over 1. Like that's just not how fractions work, right? So what I would probably do here first is start by writing things in terms of sine and cosine. If you are ever stuck and you can't see a Pythagorean identity, you can't see anything to get broken up or simplified in any way, the first thing you can always do is rewrite things in terms of sine and cosine. That will generally kind of help you progress. Even if it's not the fastest way, it will usually kind of get you towards somewhere. So I'm going to rewrite the, cosine is still cosine, but secant we can rewrite as 1 over cosine of t minus 1. Now this probably doesn't look like it helped very much, but this kind of brings us to a kind of scenario that you should be on the lookout for. So whenever you have a fraction within a fraction like this, where you're adding or subtracting something from that fraction, a good idea would be to make a common denominator within that part of the fraction. So in this case, if we make a common denominator in the denominator, so a common denominator among 1 over cosine of t and -1, that might help us to kind of take another step in simplifying this. So let's try that. So what would the common denominator be? Well, it would just be cosine of t, right? So I'm going to multiply 1 by cosine of t over cosine of t. And so let's see what happens after we do that. So we get cosine of t minus 1 over, so now we're going to have 1 over cosine of t minus cosine of t over cosine of t. Okay, so now that we made the common denominator, we can just combine those two terms in the denominator. So we have cosine of t minus 1 still in the numerator, but now in the denominator we have 1 minus cosine of t all divided by cosine of t. Okay, so where should we go from here? Well, now we're back in a situation we've been in a few times so far in this video, where if you're dividing by a fraction, you can rewrite it as multiplying by the reciprocal of that fraction. So I'm going to rewrite this as cosine of t minus 1, and I'm going to put it in parentheses, just to be really clear here, that this whole thing is getting multiplied with, now we're going to flip the denominator over, and it's going to be cosine of t over 1 minus cosine of t. Okay, so now what? Thinking back to something that has happened in some other examples, let me just scroll back up a little bit. So this was a very similar situation here, right? We had division by a fraction, and so we flipped that fraction over, and then that allowed us to cancel out the cosine squared. Where else did this happen? Here. Or no, sorry, that's not the same case, but whatever. This is a good example of this, right? That sometimes when you're dividing by a fraction and you flip it over, it enables you to cancel something out. And so we'll see that that is going to happen here, but we can't like immediately cancel. So looking at these two things here and here, these are very similar, right? One is cosine of t minus 1, the other is 1 minus cosine of t. So those are not exactly the same expressions. We can't just cancel them out like that. There's one other thing we have to do first before we can cancel. So this is another little algebra trick that is very handy to know. If you have an expression that looks something like a minus b, that is always going to be the negative of b minus a. Like, in other words, if you want to flip the order that you're subtracting something, you just have to pull out a negative sign. And you can kind of prove that that's true to yourself, right? So if you take this right-hand side and distribute the negative sign in, you would get negative b plus a, which is the same as a minus b. So how can we make use of that idea here? Well, we can take one of these, either this one or this one, and pull out a negative sign, and that will make it look like the other one. So I'm going to rewrite this as negative 1 minus cosine of t, right? Instead of cosine of t minus 1, that's the same thing as negative 1 minus cosine of t. And again, you could check that just by distributing that negative sign back in. You'll see that you get negative 1 plus cosine of t, which is the same as cosine of t minus 1. And then we're multiplying that with cosine of t over 1 minus cosine of t. Okay, so why does that help? Well, now we do have something we can cancel out, right? Now like before, they looked similar, but they weren't quite the same. We couldn't cancel them. Now we can. We have 1 minus cosine of t. We have 1 minus cosine of t. And so what is left over when we cancel? Well, this negative sign is going to be left over. And so we're left with negative 1 times cosine of t, or just negative cosine of t. Okay, getting a little bit more complicated for these next examples. So this is another kind of situation that arises with these type of problems, which is when you have multiple fractions that are getting added or subtracted. So this is something you've seen in all different parts of math, right? Like how do you add together two different fractions? You make a common denominator. So, in this case, the common denominator is going to look kind of complicated, but really the idea is the same. So what is the common denominator going to be in this case? Well, it's going to be the product of the two denominators we have, right? So I'm just going to rewrite this and put some space for us to create that common denominator. That's why I'm leaving this like big space here. So the common denominator is just going to be the product of these two denominators, right? So we want to multiply this one by 1 plus cosine of theta over 1 plus cosine of theta. And we want to multiply this one by sine of theta over sine of theta, because that's going to give us now a denominator of sine of theta times 1 plus cosine of theta. So let's multiply that, and we're going to maybe not multiply the denominator out, but let me just write all this out first. So we have 1 plus cosine of theta times 1 plus cosine of theta. That's the numerator of the first fraction. And then in the denominator, we have sine of theta times 1 plus cosine of theta. And then the other fraction is going to be sine of theta times sine of theta, so that's sine squared of theta. And again, the same denominator. That's going to be sine of theta times 1 plus cosine of theta. And eventually we may need to multiply this denominator together, but let's just leave it as it is, because in some cases, multiplying it out might make it actually a little harder to see what simplification needs to happen. So let's just kind of wait until the end to multiply the denominator together. But let's multiply the numerator out, right? So this numerator here, how would we multiply that out? Well, it's just FOIL, right? It's going to look more complicated, but it's really the same idea as your typical kind of FOIL situation. So I'm actually going to go do this off to the side to kind of give us a little bit more space. So how would you multiply out 1 plus cosine of theta times 1 plus cosine of theta? Well, that's going to be 1 times 1, so that's 1. That's going to be 1 times cosine of theta, which is cosine of theta. That's going to be cosine of theta times 1, which is another cosine of theta. And then it's going to be cosine of theta times cosine of theta, which is cosine squared of theta. And so altogether, we get 1 plus 2 cosine of theta plus cosine squared of theta. So that is the numerator of this first part. So here now we have 1 plus 2 cosine of theta plus cosine squared of theta. And then let's add that to our other fraction now, right? Because they have the same denominator, so we can add them together. And so then we're going to say plus sine squared of theta. And that is all divided by, again, sine of theta times 1 plus cosine of theta. Okay, so this next step I think is a little tricky, but notice that we have both a sine squared and a cosine squared. And so that should make you think of the Pythagorean identity, right? So what is cosine squared plus sine squared equal to? That's equal to 1. Right? All this stuff here, that's actually just equal to 1. And so we can rewrite this as 1 plus 2 cosine of theta plus 1. And then the denominator is still sine of theta times 1 plus cosine of theta. And we're almost done. I know this still looks a little complicated, but we're really almost there. So now we have 1 plus 1. Well, that can be combined into 2. So we have 2 plus 2 cosine of theta over sine of theta times 1 plus cosine of theta. Okay, so now we should have it on our mind that we're trying to simplify this, right? And I think this is maybe even like the trickiest step of this problem. But notice that in the denominator, we have this 1 plus cosine of theta, and here we have something that looks very similar. We have 2 plus 2 cosine of theta. And so what can we factor out to make the numerator look more like the denominator? Well, we can factor out a 2, right? So I'm going to rewrite this as 2 times 1 plus cosine of theta. So just factoring out a 2 divided by sine of theta times 1 plus cosine of theta. And now we're pretty much there because now we can cancel out this common factor of 1 plus cosine of theta. And so we're left with 2 over sine of theta. And so, that like is an okay answer, but in general, you want to, like, in your final answer, not use fractions if possible. And so what's another way of saying 2 over sine of theta? That's the same thing as 2 times cosecant of theta, right? Because cosecant is the reciprocal of sine. It's 1 over sine. So 2 over sine of theta is the same as 2 times cosecant of theta. And that is our final answer. So I know this problem was a lot. This brings up a lot of things. This is harder than something I would put on like a quiz or an exam, but I think it's a really good example because it really does bring up a lot of things. So maybe just to quickly recap, what was our kind of plan of attack here? First thing was make a common denominator. And, I think that step should be pretty clear because that's, if you have two fractions being added together, that's what you have to do. Once we had our common denominator, we had to multiply out, we had to FOIL this numerator, right? 1 plus cosine of theta times 1 plus cosine of theta. And so we went off and did that to the side. Then we added our two fractions together, and when we added them together, the sine squared of theta that was over here combined with a cosine squared of theta and equaled 1. And so we used a Pythagorean identity. Then we just kind of combined like terms and ended up with 2 plus 2 cosine of theta over sine of theta times 1 plus cosine of theta. And then the tricky part was kind of just recognizing that these are similar, right? That there's something you can do to make the numerator look like the denominator, and that thing was factoring out 2. So we factored out a 2, and that enabled us to then cancel out the 1 plus cosine of theta, and we were left with our final answer of 2 over sine of theta, which is the same as 2 times cosecant of theta. Okay, is this the last? Yeah, this is the last example of this kind of category. So this one is somewhat similar to the last one in that we're trying to add two things together, and really we want to create a common denominator. So in this case, how do we create a common denominator? Well, let's actually see if we can make the first part look more like a fraction. And I'm sure that this one could work out without doing that. Like you could definitely just multiply both of them by 1 plus cosine of x. But I think things might come out a little clearer if we start by rewriting this in terms of sine and cosine, because then it'll be like we're adding two fractions together. So how do you write cotangent in terms of sine and cosine? Well, that's the same as cosine of x over sine of x, because it's the reciprocal of tangent, and tangent is sine over cosine. And then we have plus sine of x, and maybe I'll leave a little space here for making our common denominator. We have plus sine of x over 1 plus cosine of x. Okay, so what's our common denominator going to be this time? Well, it's going to be sine of x times 1 plus cosine of x. So actually, that's pretty much identical to our denominator here, right? Like this looks actually very similar. We have a sine of x and we have a 1 plus cosine of x. So we're going to multiply this one by 1 plus cosine of x over 1 plus cosine of x. And we're going to multiply this one by sine of x over sine of x. Okay, so what happens when we do that? Well, then this fraction is going to become cosine of x times 1 plus cosine of x divided by sine of x times 1 plus cosine of x. And then we have plus sine squared of x divided by, again, sine of x times 1 plus cosine of x. And I feel like this one actually might come out to be pretty similar to the last one. Okay, so what should we do next? Well, we can combine the two fractions, and we can also multiply this part out. So maybe let's do that first. So if we multiply this numerator out, we get cosine of x plus cosine squared of x. And then we can combine that with the other numerator. So that's plus sine squared of x. And that's all going to be divided by sine of x times 1 plus cosine of x. So again, what happens here is we have a cosine squared of x plus a sine squared of x. We know that that is equal to 1, right? That's one of the Pythagorean identities. So we can rewrite this as cosine of x plus 1 divided by sine of x times 1 plus cosine of x. And so now we can see that we have a common factor of cosine of x plus 1 in both the numerator and the denominator. And so we're left with 1 over sine of x. And so a nicer way to write that would be cosecant of x. So really this one I think is like kind of just the simpler version of the last one, because a lot of the same stuff happened. I think the one step that maybe was a little trickier was at the beginning, we had to rewrite cotangent in terms of sine and cosine. But from there, it was very, very similar to the last one. We made our common denominator, we multiplied things together, we added the two numerators together and saw that two of the terms combined using an identity, and then we were able to cancel out a common factor in the numerator and the denominator. Okay, so we're now going to move on to some other problems. So this one is, I just added this. This wasn't originally on the activity, but I realized that there's a couple of homework problems that I didn't really do a similar problem in the video or on the worksheet. So I wanted to give you the chance to kind of see how a problem like this works out. So we're given sine and cosine of two different angles. So we have two angles, alpha and beta. Alpha and beta are angles that both have their terminal point in quadrant 2. And then we're told what sine of alpha is, we're told what cosine of beta is. We're not told the other ones, right? We're not told what cosine of alpha or sine of beta is. And so those are the first two things we're going to find. Once we have those pieces, then we're going to use some angle addition and subtraction formulas. So by the way, on the homework problem that's similar to this, they don't ask you to do this intermediate step, but you do have to do that in order to answer the question. So the questions on the homework that are similar, they give you the value of sine and cosine, and then they just jump straight to asking you to do something like this. And so as an intermediate step, what you need to do is find sine and cosine of like whatever information is missing, right? So we're given sine of alpha. That means we now need to also find cosine of alpha, and we're given cosine of beta. So we also want to find sine of beta, because as we'll see in a little bit, we need all of those different values in order to actually use the angle addition and subtraction formulas. Okay, so let's focus on the angle alpha for a moment. So we're told that sine of alpha is 1/4. We're told that alpha is in quadrant 2, and we're asked to find cosine of alpha. So this is actually going back to something that we learned earlier in the quarter, right? This is not like the most recent stuff. This is just using the Pythagorean identity. So I'm just going to sketch a rough picture to have as a kind of reference. So this is telling us that alpha is an angle in quadrant 2 and that sine of alpha is 1/4. So that means that alpha will be an angle where the y coordinate is 1/4 and it's in quadrant 2. So, maybe it looks something like this. It's just kind of my guess about what alpha could look like. So what does this point look like? Well, we do not know the x coordinate, right? That we have not found, but we know that the y coordinate is 1/4. And so how do we find that x coordinate, right? Because that's what's going to tell us cosine. That's where the Pythagorean identity comes in. So to do the Pythagorean identity, we say cosine squared of alpha plus, and maybe I'll do it without the parentheses because those get annoying, cosine squared of alpha plus sine squared of alpha is equal to 1. We don't know what cosine is, so we just have cosine squared of alpha plus, but we do know that sine of alpha is 1/4. So I'll put that in. 1/4 squared is equal to 1. And so we have cosine squared of alpha plus 1/16 is equal to 1. Let's rewrite 1 as 16/16. So then we get cosine squared of alpha is equal to, if we subtract 1/16 from both sides, we get 15/16. And then we can take the square root. And so we get cosine of alpha is equal to plus or minus square root of 15/16. And so we can simplify this a little bit because square root of 15, that cannot be simplified, but square root of 16 can. So we have square root of 15/4. And then the last step is figuring out whether it's positive or negative, and that's where our picture comes in, right? So we're in quadrant 2, and when you have an angle in quadrant 2, the x-coordinate is going to be negative, just because of where it's located, right? It's to the left of the the y-axis, and so the x-coordinate is negative, meaning that cosine is negative. And so we're going to take the negative answer, and our final answer here is that cosine of alpha is equal to negative square root of 15/4. Okay, so that answers that. Now we're going to do the same thing to find sine of beta, right? So if we go back in the information that's given, we're told that cosine of beta is negative 1/3. We're also told that beta is also in quadrant 2. And alpha and beta, by the way, they're two different angles, right? So we're not going to, we're not treating them as though they're the same angle. Okay, so this tells us that, it tells us in the problem that cosine of beta is negative 1/3. So that might look something like this, right? It's going to be an angle where the x-coordinate is negative 1/3. We do not know the y-coordinate. That's what will give us sine when we find that. So this is our angle beta. So again, we just use the Pythagorean identity. So we know that cosine squared of beta plus sine squared of beta is going to equal 1. We don't know what sine of beta is, but we know that cosine of beta, we know that the problem told us it's negative 1/3. So negative 1/3 squared plus sine squared of beta is equal to 1. Negative 1/3 squared is positive 1/9. We can rewrite 1 as 9/9, so to help us do that subtraction. Then we can subtract 1/9 from both sides, and so we end up with sine squared of beta is equal to 8/9. Then we take the square root of both sides, and we get sine of beta is equal to plus or minus square root of 8/9. In this case, the numerator and denominator can both be simplified a little bit. So we can say square root of 8/3, but additionally, square root of 8, that's the same thing as square root of 4 times square root of 2. So we can rewrite 8 as 2√2, right? Because square root of 4 is 2. So we're going to rewrite this instead of as square root of 8, we're going to rewrite it as 2√2. And so now again comes that decision of, is it the positive or is it the negative? So again, looking at where we are, because we're in quadrant 2, we can tell the y-coordinate should be positive, right? Because this point is above the x-axis. And so that means our answer is the positive one. So our final answer is that sine of beta is equal to positive 2√2/3. Okay, so now that we know these two, now we have everything we need to answer the next two. So looking through what is given and what we have, we now know sine of alpha, cosine of alpha, and we also know cosine of beta and sine of beta. We have all of those things. And it might be helpful to kind of write them down in one place, or maybe I'll just like circle all of them. So I'll circle the ones that are related to alpha in green. So here is sine of alpha. We also have cosine of alpha down here. And then we know that cosine of beta is equal to negative 1/3. And we also just found sine of beta. Okay, so why do we need to know all these things? Well, now we're going to use the angle addition formula. So as I mentioned at the beginning of the video, I'm going to give you these formulas on the exam. So cosine, or on the quiz as well as on the exam. So the first one was actually asking for cosine of alpha plus beta. And so basically this is telling us that it's going to be cosine of the first angle times cosine of the second angle minus sine of the angle, first angle times sine of the second angle. So in this case, that's going to be cosine of alpha, cosine of beta, minus sine of alpha times sine of beta. So now all we need to do is plug all these different numbers in, right? We have all of these different pieces of information, right? We know that cosine of alpha, that is right here, that is negative root 15 over 4. So I'm just going to put that in. Negative root 15 over 4. That is the value of cosine of alpha. We're then going to multiply that with cosine of beta. So where is cosine of beta? That was one of the ones that was given to us. That was negative 1/3. Then from that, we want to subtract sine of alpha. So where is sine of alpha? That was one that was given to us. That was 1 over 4. And then sine of beta, that is the one that we did last. That's 2 root 2 over 3. And so once we wrote all these down, now we're done doing any kind of trigonometry. We now just want to simplify. So we get positive root 15 over 12 minus 2 root 2 over 12. And so we can rewrite that by combining everything and just say it's square root of 15 minus 2 root 2 all divided by 12. So again, it's just kind of using this formula and then just taking all the values that we found earlier in the problem and putting them in. So like I said, on the similar problems on the homework, they don't ask you to do like these first steps of A and B. They just jump into asking you to do something like this. But notice that in order to calculate cosine of alpha plus beta, there was some missing information. This was given to us. This was given to us. But these two we had to find. And so that's why on the homework as well, before you jump into answering the actual questions, you're going to need to find sine and cosine of the angles that are not given to you, right? You're given like half the information you need. You have to find that remaining half using the Pythagorean identity. So next up, we're doing sine of alpha minus beta. So again, that's another formula that will be on your quiz. So that is going to be sine of alpha times cosine of beta minus cosine of alpha times sine of beta. So we have sine of alpha, cosine of beta, minus cosine of alpha, sine of beta. So again, once we wrote that down, now we just need to go and like find all these different numbers and put them down. So sine of alpha, that one I think was given to us, right? That was 1/4. So we have 1/4 times cosine of beta. So cosine of beta, I think that was also given to us. That was negative 1/3. And then cosine of alpha, that's one that we found in part A. So that's negative root 15 over 4. And then sine of beta, that is the last one we found. So that was 2 root 2 over 3. So combining all of this is going to be negative 1 over 12 minus negative, and actually maybe I'll just combine these and make it plus, right? Plus root 15 times 2 root 2, that's going to be 2 root 30. Right? Square roots get multiplied together. So like square root of A times square root of B is the same as square root of A times B. So in this case, we have square root of 15, we have square root of 2, multiply those together, you get square root of 30, and then we also have this extra 2 out front that came from here. And so our final answer is negative 1 plus 2 root 30, all divided by 12. All right, last set of questions. So these are again going to be using angle addition and subtraction, but these are a little bit different than these previous ones. So in these ones, we actually never knew what alpha or beta was, right? We were never told what those angles were. We never actually found what those angles were. We didn't need to know what those angles were. As long as we knew what sine and cosine of each angle was, we were fine to finish off the problem. But on this problem, we actually are kind of given angles to work with. And so in these ones, what we need to do is find a way to break each of these angles down into two kind of simpler angles that we know how to work with, right? Like we basically want to find a way to rewrite 165 degrees as something plus something. And we want both the angles we're breaking it down into to be angles that we know how to find sine and cosine of, like using the unit circle. And so maybe let me kind of write down like what are kind of the nice angles that we know how to work with. Well, we know how to work with angles like 30 degrees, 45 degrees, 60 degrees, 90 degrees. I think that's a good starting point. Like honestly, I think we can do most of what we need to with these. Although actually, let's add a little more. 120 degrees, right? That would be like 2 pi over 3. 135 degrees, that is 3 pi over 4. Let's just do a little bit more. So 150, that would be 5 pi over 6, and 180, right? Maybe just let's work with these ones and see like how can we add or subtract some of these numbers together to find 165. And there's always going to be multiple ways to do it. Personally, in this case, I think probably the easiest way to do 165 would be to break it up into 120 plus 45. Okay, so now we can use one of the angle addition formulas. So sine of two angles being added together is going to be sine of A cosine of B plus cosine of A times sine of B. And so in this case, that means we're doing sine of 120 times cosine of 45 plus, and then we flip it. So then it's plus cosine of 120 plus sine of 45. So from here, this is where it comes into play that these are kind of nice unit circle angles, right? So if I just go on the unit circle and go to angles of 45 degrees and 120 degrees, we can quickly figure out what sine and cosine are of those angles. So 45 degrees, that is where we have root 2 over 2 and root 2 over 2. So we know that sine of 45 degrees is equal to root 2 over 2, and also cosine of 45 degrees is equal to root 2 over 2. So we'll be able to put those values in here and here. But we still need to figure out sine and cosine of 120. So 120 is 30 degrees past 90, right? So like I said earlier, that's the same as 2 pi over 3. That's where we're going to have negative 1/2 and root 3 over 2. Because it's like a 30, 60, 90 triangle. And so sine of 120 degrees, that is going to be root 3 over 2. And cosine of 120 degrees is going to be negative 1/2. Okay, so now that we have all these numbers written down, now we just need to kind of put them in the right places here. So we have, first thing we have is sine of 120. So sine of 120 was root 3 over 2. Then we have cosine of 45, that was root 2 over 2. Then we have cosine of 120, so that was negative 1/2. And then we have sine of 45, which was root 2 over 2. And so if we combine these, we'll get root 3 times root 2, that's square root of 6. And then we have minus square root of 2, and that is all divided by 4. Because the two denominators multiplied together give us 4. And by the way, like I said, there's multiple ways to do this. You could have instead done, for example, let's see, 165. You could also write that as 135 plus 30. So you could try that. I would encourage you to try that yourself and verify that even though the initial setup looks different, at the end of the day, you get the same answer if you do it as 135 plus 30. So it's not like there's only one right way to do this. There's always multiple ways. So we can do cosine of 165 using the same reasoning, right? We can split it up the same way since we already have that picture drawn. So we can say, okay, this is cosine of 120 plus 45. So the angle addition formula for cosine is cosine of each of the two angles together minus sine of each of the two angles. So we have, in this case, cosine of 120 times cosine of 45 minus sine of 120 times sine of 45. And so then again, we just go back and put some numbers in. So cosine of 120 is negative 1/2. And then cosine of 45 is root 2 over 2. And then we have sine of 120. Sine of 120 was square root of 3 over 2. And then sine of 45 is root 2 over 2. And so now we just put these all together. And so we have, sorry, my screen is stuck for some reason. Oh, it's really stuck. There we go. So we have negative root 2 minus square root of 6, all divided by 4 when we put these together. All right, next up we have sine and cosine of negative 15 degrees. So again, we want to think about how we could use these kind of familiar angles to come up with negative 15. And in this case, we're going to actually want to use subtraction. So one way to do it, and probably the easiest way to do it, would be to do 30 degrees minus 45 degrees, right? 30 minus 45 is negative 15. So we can rewrite this as sine of 30 degrees minus 45 degrees. And so now we want to use the angle subtraction formula for sine. So the way that that one works is here. So sine of A times cosine of B minus cosine of A times sine of B. So we have sine of 30 degrees times cosine of 45 degrees minus cosine of 30 degrees times sine of 45 degrees. So basically, blending all the different sines and cosines. And so we already had figured out what sine and cosine of 45 degrees are. Maybe let's add 30 degrees to our picture so we can refer to that. So for 30 degrees, we have root 3 over 2 and 1/2. And so sine of 30 degrees is the y coordinate, right? That's 1/2. And then cosine of 30 degrees is the x coordinate, which is square root of 3 over 2. Okay, so we can now put these pieces together. So sine of 30 degrees, we just found that one, that was 1/2. Cosine of 45, we wrote that down earlier. That was square root of 2 over 2. It's here. Then we have cosine of 30. So that one is right here. That is root 3 over 2. And then we have sine of 45 degrees. We found that one earlier. That was root 2 over 2. So if we multiply these together, we end up with square root of 2 minus square root of 6, all divided by 4. And you might notice a lot of these answers look very similar to each other. I mean, it's really because all of the kind of angles we're going to be coming up with here are going to be sums and differences of multiples of 45 and 30. And so that, it's always going to involve both square root of 2 over 2 and square root of 3 over 2. And so that's where the square root of 6 comes from. It will also involve 1/2. That's where the just plain square root of 2 comes from. So that's why all these answers look really similar. One thing I want to point out is that you might notice that these two are exact opposites of each other. Or actually, sorry, that's not true. I take it back. This is actually the exact opposite of if this was a plus instead. What is true? I think this one is the exact opposite of actually this one. And so that we can kind of confirm, actually, never mind. Let me not get into that because I think that will just maybe feel a little confusing. But yeah, basically, if you were to, I'll just kind of briefly tell you, if you were to try to graph what 165 degrees and what negative 15 degrees look like, If you compare them, you should see that their value for sine looks like it is just the complete opposite of each other because they're directly across from each other on the unit circle. Okay, finally we have cosine. What color have I not used yet? I'll use magenta. Cosine of negative 15. So again, we already established that we can write negative 15 as 30 degrees minus 45 degrees. And so in the case of cosine, the formula is going to be cosine of both angles multiplied together and then plus sine of both angles multiplied together. So we're going to have cosine of 30 degrees times cosine of 45 degrees plus sine of 30 degrees times sine of 45 degrees. So again, it's just now a matter of putting all these numbers in. So we already know that cosine of 30, that's square root of 3 over 2. Cosine of 45 degrees, that is here. That was square root of 2 over 2. Hopefully that's not off the screen. So that's square root of 2 over 2. Sine of 30 degrees, that is 1/2. And then sine of 45 degrees, that is this one. Oops. Square root of 2 over 2. And we can combine these now, and we end up with square root of 6 plus square root of 2, all divided by 4. And so this one actually, kind of similar to what I was saying before, this is the exact opposite of our answer on the second one. And so similarly, if you graph 165 degrees and negative 15 degrees and compare what cosine is for them, you'll see that they should be complete opposite values because they're like directly across from each other diagonally on the unit circle. All right, that is it for this video. Let me know if you have any questions, and I'll see you all later.